Hey guys, it's me. I'm back and I have a problem here. Alright, so say, just for fun, that we've got a giant red slash pink or maybe salmon color cannon and we have it set so that it will fire at 60 degrees. Now we've got a castle in front of us and we want to shoot a flaming fireball into the castle. We want it to land inside the castle, but we want it to really get over the first wall. And the castle is 100 meters away from our cannon, and we fire it at a velocity that will get the fireball to the initial kind of the first wall of the castle in 2 seconds, right? So it'll fly, boo, one, two, and after 2 seconds, it'll be right above kind of the front door of the castle. All right, so we want to get it kind of inside. And the castle is 6 meters tall, plus an additional 1 meter for the arrow slots for their archers. And so I want to not only get it over kind of the initial 6 meters, but also above the archer slots, because I wanted to get it in and into the middle of the castle. So I want to know first so the first problem is, what is my initial velocity that I will fire the projectile, so that I have to get so that I will that it will take to get it into the castle. All right, initial velocity. I'm going to use my autumn colors. Where'd they go? They were just here. Oh, there they are. Okay, sweet. So let's go ahead. We'll use orange, and we'll go initial velocity, 0.25 meters. Perfect. Okay. So we know that this distance here is 100 meters. I'm going to cover that 100 meters in 2 seconds. And we'll say that our origin is kind of like right here, maybe like on the ground, like right there, right? So we know that our initial velocity, we want to find our initial velocity. We know our initial position, x, and y are both 0, right? So they're not moving, or they haven't been moved from the origin yet. Let me just erase. Boop, boop, boop. Sweet. Okay. So we can use our equation that the final position is equal to the initial position, which is just 0, plus the initial velocity times time. Right. So why am I using the final position? Well, I want to know this initial velocity here, right? And if I can say, based on this information and this information, that the horizontal component of that velocity is whatever it is, and then the object will be here at time t equals 2, right? So essentially what I'm doing is I'm saying, okay, if I knew the total initial velocity, then my final position at any time t, especially at t equals 2, is going to be 0 plus the cosine, because it's the x direction, the cosine of theta, in this case it's 60, times the initial velocity, right? And cosine theta times the initial velocity, that's just velocity initial in the x direction, right? Because we're taking the triangle of the velocity, right? If this is a velocity, that's its component in the x direction, that's its component in the y direction, and this is just, this is v initial, and so this is v initial in the x direction. It's theta, the cosine of theta times the initial velocity, because the cosine of theta is the initial in the x, or is the initial times that. Anyway, I'm getting a little bit ahead of myself. So we have our initial velocity in terms of our angle, and we also have time. In this case, time is at t equals 2 seconds. Initial velocity times 2. And we know that our final position is actually 100 meters away, 100 meters. So now we only have one variable, and we're saying that the final position, we can go 100 meters downrange based on our initial velocity, or the x component of our initial velocity, or the cosine of the angle times the initial velocity at t equals 2 seconds. So that's kind of what this equation is set up and how we're going to use it. So, scrolling down and pulling out our calculator, we can say that the cosine of 60 degrees times 2, those are both constants, so we can move them over to the other side and divide by them. So 2 cosine 60, so that we know, kind of isolating that, so we can say that the initial velocity, and again, this is just straight up the initial velocity, not the components. So our initial velocity is 100 divided by 2 cosine 60. So 2 cosine 60. 2 cosine 60 is actually 1 because the cosine of 60 is a 30, 60, 90 triangle. So it actually just is 100, and 2 is in seconds, so 100 meters per second. So that was rather nice. Worked out to be a nice round number. I did not intend that, but sometimes physics just smiles on you. All right. So, I'm not really sure what happened there. We erased our theta. Oops, wrong color. We erased our theta here. I'm having troubles with this. Bear with me, please. Anyway, yeah, so we now know that our object was fired at 100 meters per second at a angle of 60 degrees, and so it went 100 meters in 2 seconds downrange, right? Because we can take our initial velocity, we'll switch colors, maybe go to my festive colors, we'll go blue this time. Now we can say, based on our full initial velocity, we can say that the velocity initial in the x direction is equal to, like we had up here, is equal to the cosine of the angle, in this case it's 60, times the initial velocity. So in this case it's 100 cosine 60, that's 60 degrees. Make sure your calculator is in degrees, and the cosine of 60 again is 1/2, which is why that denominator ended up being 1, because it was 2 times 1/2. So that's just 50 meters per second. Sweet. Okay, so we know that we have our initial velocity is going 100 meters per second, and this component is 50 meters per second. So we can also find our initial velocity in the y direction, which is the sine of 60 times the initial velocity, which is 100 sine 60 times the initial velocity. And again, the sine of 60 times 100 is going to be something a little less nice. It's actually 86.6025403.8 meters per second. And again, in all of your calculations, I highly recommend you never round that number right now. Leave it in your calculator and only round at the very end, because that's how the majority of little tiny mistakes, they add up over time when you do calculations with, like, if you just said 86 or you said 86.6, both of those calculations, they will end up with errors in your answer. So I highly recommend you either write the whole number down or preferably just work with it all in your calculator. And that's how we can do that. So that's part A. We can move to part B and we can say, okay, I want to know how far, right, at t equals 2, I want to know how much I'm clearing by. Right? I want to know the distance from here down to the top of the outpost. And so the way I can do that is I can say, okay, move over, zoom in, sweet. Okay, so I can say that so now we're working in y, so I can say my final height, right, y final, is going to be equal to y initial. And now we're working with gravity, so we can say the initial velocity, the component of the initial velocity in y times time plus 1/2 acceleration due to gravity, so a sub g times t squared. Perfect. So again, we're starting from our origin, which is 0, 0. So that component actually ends up going away. We're working with t equals 2 seconds because that's the time we want to find, and we're trying to find the initial height. So we can go ahead and say that this is equal to the initial velocity in the y component, which we said was this 86.6025438. So I'm just going to, I have it in my calculator, so I'll just keep it as y, I, or v, I, y times 2 seconds plus 1/2 times negative 9.81 meters per second squared times 2 seconds squared, right? So our final position, again, we know this value. If we plug all this into our calculator, we're actually going to have our 86.6025438 times 2. That's going to give us this 173, oops, not 130, 173.205, etc. Again, keeping all that in our calculator, and then we have 0.5 and 1/2 times negative 9.81 times 2 squared, which is 4. And so we'll get, actually, this is a negative 19, oops, not 9, 19.62. Again, we use 9.81. We can use a longer number if we want, but I think 9.81 is almost always going to be good. That's what they use on the AP test for most physics exams. That's what most college professors will have you use. But again, that number actually depends on where you are on the Earth, on what planet you're on, kind of all that good, fun stuff. And so if we simply add those numbers together, again, using the entire full version of both of those we keep in our calculator, we get that our final height is going to be 153.5850808. And I think I had, we don't really care about sig figs. So we'll just round that. We'll say that's about equal to 100 and maybe 54 meters. So we're flying really high above this castle. After t equals 2 seconds, we're really arcing up there. So maybe we might want to tone it down a little bit on our angle. Sweet. Okay. So that is a good answer. Let's move on to the next part. Actually, I wanted, so this is, we're not done yet. I wanted to know this orange part here, which is the height minus the height of the castle. And the height of the castle is 7 meters. So our final answer is actually 154-ish minus 7 meters. And so 154 minus 7 is 140, oh dear, 147. Try to make sure on my calculator. All right, we've all been there. So 147 meters, that's your final answer, not that 154. So that is the height above the castle wall. So that's this height right here. That's 147 meters. And again, we said that this initial velocity was 100 meters per second. So 100 meters per second. That's awesome. Okay, I'll switch colors one more time. We'll work out a third problem. And I think this problem is, the third part of the problem is probably the funnest part. It's also the part that I think might be one of the hardest parts. So I want to know how far away from this wall of this castle is my projectile going to land, right? So if it's way up there, it's like 147 meters above the castle. So I want to know kind of how far this way it's going to land. So I'm projecting it's probably going to be, pretty far along. But I want to know kind of this measurement here that I just drew in orange. So now we're working back in x. So we'll say that the final x position is just equal to the initial x position plus the velocity initial in the x direction times the change in time. Right, we could say plus 1/2 at squared, but we're not accelerating in the x direction, so we're not going to use that. And we also don't have any initial position because we're starting at the origin. So the final position at some time, which I don't know, we're going to have our formula VIx plus t. The initial velocity in the x direction is actually 50 meters per second. And again, we don't know that time. Okay? So how are we going to find the time when it's hitting kind of this floor here, right? So assuming this castle goes, is infinitely wide, so it will definitely land somewhere 6 meters above the Earth. We can go ahead and we can use our function we had in the last problem and find out when this projectile will reach 6 meters, right? So if I graphed this in my calculator, right, so maybe this is my x-axis and this is my y-axis, and this forms a parabola that looks like this, right? I want to know, so maybe this is 1, 2, 3, 4, 5, 6, so that's 6 meters. Actually, 6 meters is probably down here. So it's going to cross from one time when it's 6 meters going up, and then one time when it's 6 meters going down, right? So we're going to have two zeros of this function, and I want to know the one that is greater. Okay, I'm going to go ahead and erase all this. And so I hope that kind of makes logical sense. We can graph our parabola in projectile motion, and it should be pretty reasonable to assume that, if we have two zeros, we can set it and we can find a time when the height, the y-axis, is going to be something that looks familiar to us. Sweet. Okay, so now we have the velocity. Yeah, actually we'll do this color. See if we can see it. Yeah. Velocity initial in the y final is equal to, again, the initial position. We don't have that, so we're just going to omit it, times time plus 1/2 acceleration due to gravity times time squared. And so, again, what we're plugging into our calculator is we're saying, okay, so I want the final position to be 6 meters, and I want the initial velocity to be this, 86 number times some time plus 1/2 times 9.8, so we're going to be subtracting 4.9 meters per second squared times some t squared. We can move this 6 across and put it over here, so it makes this just 0, right? So if we solve for the zeros of this equation, we're going to end up with, right, when it is 6 meters going up, and again, when it's 6 meters going down, and we want this one because that's when it's hitting kind of the building that's sitting here. I hope that makes sense. And so we're going to go ahead and put it into our calculator. We're going to hit y equals and go ahead and just plot this. We have 86t minus 4.9 t squared minus 6. And then we'll go ahead and say second calculate 0. And then we'll try and find where along the x-axis we're actually going to reach. And so sometimes you might need to expand your window a little bit, just in order to see kind of where the function is going to lie. And once we do that, we'll end up finding that our t squared, or our t, is going to be, give me a second. Yeah, so we can hit second calculate, and we can actually end up finding our second calculate, and then go down to 0. You can move your left bound so that you kind of know you're within the bounds of your graph. And then you can make a guess on most TI-84s. We have t equals 17.48097.3, and that keeps going on. But that's as much as my calculator gave me. So we know that that is the time, again, when it comes, it first crosses here at some time, but this is the time describing this when it's landing back at 6 meters and hitting that building. Okay, so then we can plug this back into our initial position function. So we have x final, I can go and do that color. We have x final equals our 50 meters per second. That's exactly 50 meters per second. Times time, which is this t here, so 17.48. We have that is 50 times 17.48097.3. We'll make sure that we're using all of those digits here. We don't care about significant figures until we get to our final answer, and then we can use significant figures. We want to make sure that our answer here is as accurate as possible, and so we're actually 874.0 meters downrange. So we'll just go ahead and say that's 874 meters. And that's how you solve it. Okay, so here's kind of what we've been doing. We started, this is part A over here. We found the initial velocity. The way we found that's not A, that's B. The way we found the initial velocity is by saying that, okay, so say I have this angle, and at that angle I'm going this many meters in this many seconds. That's a meter per second at a given angle. We can solve for how much horizontal motion we have using this equation here, which is just derived straight from that, and derived from your trigonometric identities with this cosine here, and that gave us 100 meters per second. Knowing that it's a 30, 60, 90 triangle, or you can just again use your trig here. We know that the cosine, or the x initial velocity, is 15 meters per second, and the y initial velocity is the sine of 60 times vi, which is not a perfect round number. It's actually 86.6, and that number goes on forever, meters per second. So that was the initial velocity, and we also found both its components. We also know that we have 147 meters on its height, and we found that by just plugging in the values we knew for our y equals the final y position function. It's pretty self-explanatory, and I think it also is pretty intuitive. The projectile starts here, it goes up to some height, and it comes down, and then it stops at the 6 meters, or I guess it goes up and comes down and stops at 6 meters there. Again, all of this is totally independent of a max height. We also don't need to calculate the final velocity or the initial velocity. Both of those things don't matter in the context of what we're trying to solve for. So we can actually, it's really is just plug and chug from here on out. So next is part C. This one's probably the most difficult problem because we have to use two different equations in the same problem. So the first equation is getting us set up. So we know that for some time t, any time t actually, we're moving with a velocity, a constant velocity that goes that way and only that way. We want to find the time t when it's actually hitting here, so we use our height problems. We use our height functions and say we're trying to find the zeros here and then the 0 here again when it hits, and we use that time t, plugging it back into our x equation function and finding the total distance that it traveled. So it traveled 874 meters, and so our final answer is actually going to be 874 meters minus 100 meters, which is this 100 meters. So the distance from here over is actually going to be 774 meters downrange. 774. And again, this answer here is where you would apply your sig figs. Don't apply sig figs here. Don't apply sig figs here. Don't apply sig figs here. You want to keep those answers as accurate as possible because it might actually affect your the answer that you have. All right, sweet. And have a good day.